In regards to Earth and the universe, we cannot separate the physical existence we enjoy from the necessary cause for its origin. Likewise, we cannot separate the physical matter of the universe apart from the physical laws that govern its behavior. And as we observe the order and design in our incredible universe, we also see that we cannot separate the function and the complexity and still maintain the fine-tuned balance of the entire system. Now, when we look at our universe, we see a fully functioning, complete system, from the largest galaxies to the smallest bacteria, from the vast multitude of existing stars to our single, complex planet Earth. And of all the places to consider, it is here on Earth where the full functionality and completeness are most obvious, especially demonstrated in pristine clarity in the processes of life. The multitude of necessary systems and physical cycles form a web fine-tuned for life. If one cycle or condition is missing, then life's possibility vanishes. So when we observe and evaluate our amazing existence here on Earth, and we consider what best explains the mountain of evidence for function, complexity, order, and design, that of an intelligent and purposeful creator provides the consistent answer, one that the random, chaotic, mindless evolutionary processes cannot. But what does the necessity of a fully functional cosmos tell us about its age? How old is the universe? First, being the product of an intelligent creator, we would expect each physical process within the universe to have all of its constituent parts, both matter and law, from the very beginning of creation. The precise characteristics of subatomic particles like protons and neutrons and electrons, they must exist simultaneously with the physical laws of electricity and magnetism. The existence of radiation, such as heat and visible light, must exist simultaneously with the laws of thermodynamics. And for life to exist on Earth, there must simultaneously exist all the fundamental laws of nature, along with all the forms of matter on which life depends, from the basic atoms to the highly complex molecules. The universe and Earth, therefore, were created in a mature form with fully functioning processes. And for life on Earth, our observation of its design tells us that life could not have waited billions of years for the sun to evolve, for water to arrive, or the atmosphere to stabilize. Rather, all of the processes on Earth are so interdependent and fine-tuned that they must function together. Life exists within the precise arrangement of Earth's cycles, which only exists within the precise arrangement of the Sun, Earth, and Moon system, which only exists within the precise order of the universe's laws. The timing for the creation of life and planet Earth was synchronized from their beginning. Observing that life, Earth, and all the natural laws of the universe have a common beginning provides us their relative ages. That is, relative to each other, they have the same age. Now, this is a very important observation because it serves as a distinguishing characteristic for the history of our cosmos. Was the history of our cosmos one of a long, slow, incremental development where separate fundamental processes were accumulated and set in motion billions of years apart from each other? Or does a coordinated beginning, where physical matter, natural law, life-sustaining processes exist together, provide a more accurate history for what we see? Here, our inquiry has shown us what the relative age and the history of the universe looks like, one which matches the history of creation that the Bible describes. In the beginning, God created the heavens and the earth. In short succession, the earth was formed and fashioned for an atmosphere, for a water-dominated surface, for the existence of plant and animal life, and for mankind. Earth and its systems were created together to function in a physical relationship with the sun, the moon, and the stars, all designed as complements within a functionally complex universe. Now, the next question that follows then is, when did this common created origin happen? Was it billions of years ago, or was it a time span more in line with the records of human history? Well, scientific study is excellent for making comparative observations, for relating the quantities and values and characteristics of different components. However, science requires a standard or a set of known values when establishing an absolute measurement, such as an absolute age. Yes, we can record the time of events that we directly observe, such as how long a process took to complete from start to finish. Yes, we can pinpoint events in civilization's history through the records of participant observers. But what about when we do not have firsthand records or firsthand observations? Well, this is where we use the power of scientific comparison. We perform a firsthand experiment and we use this known observation as a standard to compare to what we have not seen. For example, having studied the life cycles of animals around the world, we can identify the age of a living creature, even though we did not see it born. We can look at various plants and understand the limits of their age by comparing previous life cycles that we've observed, from seed all the way to maturity. However, when it comes to an entire planet like Earth, relative age comparisons fail. We have never seen one, let alone repeated, full development cycles of an entire planet. Do we see other planets in the universe? Yes. Numerous others are right here in our own solar system. But apart from the living organisms on Earth, the structural makeup of our planet is not living. Planets are not truly born, they do not develop through adolescence or grow into maturity, and they do not die, ceasing to exist. Rather, like a rock that you hold in your hand, Earth itself is made of inanimate matter. It exists in a certain form now and can over time, through internal or external processes, have some alteration to its form, but the rock is still a rock. What this means is that science does not offer some absolute age marker for the universe. Merely it limits on internal processes. Yet it absolutely provides evidence for its designed origin and the level of intelligence and power and authority of its creator. The Bible then comes into our discussion as an externally and internally verified source of divine information. When we look to its record for when the universe came into existence, we see the focus of Scripture being Jesus, the Son of God, who lived roughly 2,000 years ago. His parents' lineage is clearly recorded, stretching back through the royal line of David, back to the beginnings of the tribe of Judah, the great-grandson of the patriarch Abraham, who lived about 2,000 years before Christ. Following Abraham's lineage, we trace back through Shem, the son of Noah, who was saved from the catastrophic global flood. From Noah, we trace back through men like Methuselah and Enoch until we arrive at Seth, the son of the very first couple, Adam and Eve, who were created by God in the Garden of Eden roughly 2,000 years before Abraham, 4,000 years before Christ, and 6,000 years before our current time. The Genesis record provides for us the culmination of the cosmic creation period. So God created man in his own image. In the image of God, he created him, male and female, he created them. Then God saw everything that he had made, and indeed it was very good. So the evening and the morning were the sixth day. As the New Testament states, and he has made from one blood every nation of men to dwell on the face of the earth, and has determined their pre-appointed times and the boundaries of their dwellings, so that they should seek the Lord. Humanity's common origin, then, was on the sixth day from the common origin for our planet Earth and the cosmos. This historical event, as described biblically and consistent scientifically, occurred only thousands of years ago, not millions or billions. We often use the word cosmos as a single name used to identify the existence of all matter. Every atom, asteroid, planet, galaxy, and even space itself. But in addition to simply referring to the existence of all space and matter, the word cosmos is used because it describes the observed order and design in nature. The ancient Greeks, as far back as the 6th century BC, used their word for order, cosmos, to describe what they observed in the world around them. If ancient cultures, prior to the understanding of electricity, magnetism, radiation, optics, subatomic interactions, or even the equations of gravity, could make and conclude that order and function existed, then how much more should our generation appreciate the functional complexity of the universe? You see, our universe does not exist as a chaotic collection of space and matter. Rather, the ordering of our cosmos can be seen from the very fabric of space-time itself. The physical laws that govern matter supply the foundation of functionality that we observe. From the beginning of time, mankind has explored, slowly constructed a detailed understanding of the physical world so that we can construct experiments, forecast expectations, and successfully predict results. But our mathematical expressions and the formulas are merely descriptions for how the laws naturally operate on their own. Our scientific investigations only reveal what order and function the cosmos inherently has. The functional laws of the universe exist, whether we can describe them, whether we can write them down, or whether we even know about them at all. Now, when we observe nature, we're not observing the physical laws themselves. Rather, we observe the functionality of our cosmos through the diversity of its complex structures. Along with space itself, matter fills the cosmos, forming a breathtaking array of complex structures. From subatomic particles to spiral galaxies, from the trillions of cells that compose the human body, to the seething plasmas that power the stars. Complex order is found at every cosmic scale. Take, for instance, the simple periodic table of the elements. This singular chart is mankind's expression of the orderly sequence of elements that form the building blocks of our material world. Each element has a unique identity in its nuclear structure and fundamental characteristics. The periodic table uses both a periodicity and related groupings to visualize the comparisons and the contrasts among all the elements. For instance, the number of protons in an atom, called the atomic number, is a unique property for each element, and it forms an increasing sequence from left to right and from top to bottom. The overall structure of the periodic table includes horizontal rows called periods, which are arranged to identify the highest energy level of the element's outer electrons. The vertical columns are groups or families, and they help to identify elements that have similar chemical properties. In fact, the orderliness of our cosmos is so well displayed in the periodic table that when early scientists were developing its structure from all the elements that they knew at their time, they found gaps in sequences where obviously an element should exist. These gaps in the ordered sequences led to numerous discoveries of elements which had not been known before. Had these new elements always existed? Absolutely. But until we identified the ordered structuring of matter, we could not correctly identify and describe the elements. The periodic table has elements that are the building blocks for the host of complex structures in our cosmos. Yet these complex structures, in turn, are participants in an equally inspiring set of complex interactions where cosmic laws exert their influence through the forces of nature. Here is where the complex nature of the cosmos has both confounded and astounded humanity. As much as we would like it, the physical laws do not obey human whims. We're subject to their processes and governed by their operation. No matter what branch of scientific study, what scale of experiment, or what object of observation, the complex matter being observed is influenced by a host of physical laws and principles. So in our scientific experiments, while we struggle in confining the matter or painstakingly restricting its contamination and seeking to establish boundary conditions, we must acknowledge that without the regular and ordered functionality of the laws of our cosmos, the complexity we see would merely be chaos. No scientific understanding could be obtained, let alone even initiated, if the regular, repeatable, and restricting laws were not present and functioning. If the origin of matter and energy, let alone the construction of complex structures, cannot emanate from the matter or energy itself, and if humanity doesn't control it, let alone establish the cosmic law, what does the presence of both law and matter, function and complexity demand? The evidence leads to an intelligent creator of such power and magnificence that the beauty of the cosmos, in all its order and function, pale in comparison to him. The night sky is a great equalizer for humanity. No matter who you are or what your background is, when you stand beneath the night sky, looking out into the vast darkness of the heavens, our humanity experiences a sense of awe and is filled with wonder. When we consider what is beyond the stars, the mere existence of space conveys a necessary pre-existing cause. But our cosmos is not merely a small assemblage of space. Rather, it is vast, reaching distances that boggle the mind. Come with me on a quick journey to explore the size and scale of the cosmos, marked out by the matter that fills it. Beginning with the region that surrounds us, we see the scale of our everyday lives, those aspects of our lives on Earth, commonplace to us. As we expand out, we see that our own planet has terrain and topography, forests and waterways, and differing habitats for life. Beyond the mountain ranges and landforms, we find the structure of continents and oceans that compose the entire globe of our planet. At this point, our field of view is only about 10,000 miles wide, and while it encompasses everything that comprises our lives, we are only seeing one object in space. Moving away from Earth, we see our nearest neighbor, the Moon, come into view. At a distance of 240,000 miles, this rocky, airless body is our nearest neighbor and is the brightest object in the night sky. By the time our field of view includes the Sun, the nearest star to Earth, we are able to see the orbits of the two innermost planets, Mercury and Venus. Located about 50 million miles outside of Earth's orbit, we find our neighbor Mars, the red planet. And thereafter, we see the asteroid belt forming the boundary, separating the orbits of the inner terrestrial planets from the orbits of the outer gas giants, Jupiter, Saturn, Uranus, and Neptune. We have now reached a field of view encompassing all of our solar system, out to the dwarf planet Pluto and its several moons. Our field of view at this point is almost 7.5 billion miles, yet only contains one star, 8 planets, a few dwarf planets, asteroids, and comets. It is not until we have many stars in view that we even begin to see that there are large clouds of gas, called nebulas, that become visible. Continuing to accelerate outward, we see the structure of our own Milky Way galaxy, with its spiral arms encircling a dense nucleus. Our field of view is now 100,000 light years. Now we are viewing distant points of light, which are not stars but are large collections of stars, gases, and dust, known as galaxies. Each of these galaxies likely contains billions of stars, like the one our planet orbits every year. Finally, at the largest scales to the universe, we see that even galaxies are organized into groups, clusters, and superclusters. Seeing the cosmos from its smallest to its largest scales, we get a view of just how vast it is. When we consider all that is beyond the stars, is it reasonable to conclude that everything we observe is merely the result of chance and chaos? Or that a random, unguided, non-intelligent origin provides the greatest explanatory power for why we are here? Few people in their lifetimes will travel very far around our single planet. Rather, we expend much of our energy and our intellect to build shelters for our families, buildings for our communities, and infrastructure for our countries. We recognize that the physical structures around us require intelligence and design and effort. But these man-made structures pale in comparison to the physical structures that exist and populate our entire universe. Their existence requires the same recognition. That is, that we inhabit a grand cosmos created by an intelligence of such greater proportion than even the size and scales we see. Life is a balance of needs. We expend much of our effort in scheduling to fulfill the basic needs of our existence, providing the fundamental necessities of water, food, and shelter for us, and those that depend on us takes effort and planning. But what about nature and the complexities of the cosmos? Do we schedule or attend to the laws of nature? Do we provide what is needed for everything that is out beyond the stars? We live our lives as participants within the cosmos. While fulfilling our role, we are able to observe and enjoy the beauty of our cosmos through the elegance of its finely tuned arrangement. The elegant fine-tuning that exists within the cosmos can be seen by the host of interactions happening all around us. Science tries to mirror that natural elegance through the mathematical expressions we use to describe the processes that we're observing. For instance, the gravitational relationship between masses forms the basis of our understanding for all cosmic motion, including everything from planetary orbits to galactic dynamics. The equation describing gravitational force between two objects includes three important factors. First, the masses that are involved, which addresses the existence of structure. Second, the distance between those masses, which addresses the existence of space itself. And third, Newton's universal gravitational constant, a fundamental physical constant that addresses the scale of this force. Both the relationship between mass and distance in this equation, which scales directly with mass and inversely with the square of distance, and the presence of the gravitational constant show a finely tuned balance for the overall strength of gravity's force. Why is it that gravitational interactions follow this relation? Why inversely with the square of distance rather than a direct relationship? Why is the universal gravitation constant the value that it is? These are questions which humanity does not decide. We have discovered the relation, and we have assigned the units by which we measure it, but we did not decide for the cosmos what form of relation or what scale the gravitational force should have. Current understanding categorizes the interactions of nature into four fundamental forces: gravitational, electromagnetic, strong nuclear, and weak nuclear. Each of these forces has a relative strength and scale of operation that is finely tuned to balance the others. The relations of these forces depend on the finely tuned arrangement of our cosmos, from the material constants, such as mass and charge of elementary particles, to the spatial relations for how each force is exerted, to the universal physical constants that balance their effects. The scientific pursuits of investigation and exploration are thrilling, from the discovery of subatomic particles to mankind taking its giant leap on the surface of the moon. The complex nature of the universe has both confounded and astounded humanity, yet the fact that such a vast cosmos exists, that its complexities function so precisely, independent of any human intellect, demands that an intelligent creator designed, and ordered this finely tuned cosmos that we are now privileged to study. Every day we benefit from the sun's consistent nature. The sun rises and sets, and our globe is bathed in its constant and sustaining energy. Life's very existence depends upon the light that Earth receives and the well-balanced parameters of the sun's size, its temperature, distance, and mass. All of them very important to the sun-Earth relationship. First, in terms of its physical size, the sun is by far the largest object in the solar system. The sun is approximately 10 times wider than Jupiter and over 100 times wider than Earth. Its volume could contain around 1 million Earths. The sun is also a massive object. If you were to add together all of the mass for every object in our solar system, the terrestrial planets, the gas giants, the dwarf planets, all of their moons, the asteroids, the comets, the sun by itself would still be far more massive. In fact, the sun contains 99.866% of all the mass in our solar system. Being the most massive object, the sun acts as a gravity anchor, holding all the planets and dwarf planets and objects in their respective orbits. From our perspective on Earth, the sun appears as a bright yellow disk. The part of the sun that we can see shining so brightly is called the photosphere. This layer is often described as the visible surface of the sun because it's the outermost opaque layer, restricting our view of the sun's deeper layers. Now, while we use the term surface, we're not saying that the sun is solid. Rather, that the sun is composed primarily of hydrogen and some helium in a very highly energized state of matter called a plasma. The photosphere has a temperature of 10,000 degrees Fahrenheit, and it radiates dominantly visible light. If you were to take a picture of the sun, your picture would show a mostly featureless ball. But remember, don't look directly at the sun without special protection. The sun emits all the colors of visible light: reds, oranges, yellows, greens, blues, and violets. If all of these colors were equally emitted, then the sun would appear a very bright white. But instead, the sun appears a yellow because the peak wavelength of its output comes from the yellow range. The spectrum of sunlight that Earth receives is finely tuned for life to thrive. The sun's visible light outputs peaks in the yellow-green range of wavelengths. The solar spectrum effectively covers the major wavelengths needed for photosynthesis. This absorption of specific wavelengths of sunlight powers the critical, life-sustaining process of our planet. Earth would not be able to support humanity and the abundance of all the other life if this single process of photosynthesis did not function and proceed at its effective level. Keep in mind, the visible light you are seeing is only a small portion of the full spectrum given off by the sun. Visible light is only a particular radiation energy range in the full electromagnetic spectrum. Every day we encounter and even use many of the other energy ranges, from listening to the radio, to popping popcorn in a microwave oven, to the infrared motion sensors in our houses, or having an X-ray image taken of a broken bone. The sun actually gives off varying amounts of all of these energies. The amount of energy that Earth receives from the sun is approximately 1,400 watts per square meter on our surface. It is so consistent that it is referred to as the solar constant. Aspects of the sun's design can be seen in its consistent nature, both in its role as a gravitational anchor for the solar system, including Earth's stable orbit, but also in its role as the constant source of Earth's life-sustaining energy. But the sun is not silent. It has a dynamic nature as well. And the sun's dynamic nature provides a view of its complexity and its design. The surface of the sun is constantly churning like a pot of boiling water. Large columns of matter rise from the hot interior while cooler regions sink back down. This convective motion creates granulation, an effect seen at small scales within the photosphere, where cell-like structures or granules form with hot matter surrounded by cooler boundaries. While we are usually only aware of the sun's consistency from day to day, the sun actually teems with activity, from sunspots to massive eruptions. Sunspots are large dark regions on the sun's surface. They form due to the sun's intense magnetic field. The disturbances cause the surface material in that region to slightly cool and appear darker in contrast to the rest of the photosphere. The interior of a sunspot is still extremely hot, only a few thousand degrees cooler than the rest of the surroundings. The number of visible sunspots fluctuates through a solar cycle, and this cycle follows an 11-year oscillation from a period of low activity, called a solar minimum, through a period of high activity, called a solar maximum, and then back to the minimum. During a solar maximum, there can be hundreds of sunspots, and sunspots are often the precursors to a variety of other active features. Outbursts of hot gaseous material can occur from the magnetically disturbed sunspot regions, extending thousands of miles above the surface, forming prominences and filaments, coronal loops, coronal streamers, and even coronal mass ejections. These larger, outward extending features occur above the photosphere in the sun's less dense upper atmosphere. Prominences and filaments are two features mainly seen within the chromosphere. And essentially, they're the same features seen either face-on or at an angle. Prominences can appear as dramatic bursts of material looping off the side of the sun. The looping path that the material takes follows a strongly distorted portion of the magnetic field. Similarly structured to prominences, coronal loops are even larger extensions of heated material that follow magnetic field lines extending out into the sun's atmospheric layer called the corona. Amazingly, this outer atmospheric layer reaches temperatures of 1 to 2 million Kelvin, being superheated by the solar wind and the magnetic storms. Sometimes we use the term space weather to describe various fluctuations and changes in space, especially that affect us here on Earth. Most of these fluctuations originate from the active nature of the sun. The mechanism that drives the occurrence of space weather is a feature known as the solar wind. While space within our solar system is nearly a vacuum, there is a continuous flow of particles streaming outward from the sun, and this forms what we call the solar wind. A continuous wind of particles that travels at incredible speeds, 1 to 2 million miles per hour. However, episodes of extreme space weather occur whenever a coronal mass ejection or a CME event occurs on the sun. CMEs are concentrated bursts of highly energized matter that is ejected from the sun in these eruptions of solar flares. If such an event happens in the direction towards Earth, then we are showered with literally hundreds of millions of tons of charged solar particles. Though the sun can be wildly active, can cause extreme space weather conditions, its dynamic nature actually helps to demonstrate just how privileged our planet really is. We live day to day with very little noticeable impacts into our lives. And some of the most observable consequences to this intense solar activity are the beautiful auroral lights that dance across the skies near the Earth's polar regions. Remnants of the massive solar eruptions that were safely deflected by Earth's magnetic field. Yet these few particles that were caught spiral down and interact with atoms in our ionosphere, releasing emissions of visible light. Earth's protective layers of safety were designed in concert with the sun's nature to supply what is needed for humanity's existence. Mercury is the smallest planet in our solar system. In many ways, it appears similar to our nightly companion, the Moon. Visually, Mercury has a rocky body, heavily cratered, and it lacks any visible atmosphere, which is strikingly similar to our Moon. But Mercury is a planet of extremes, existing in its own unique place in our solar system. Being the innermost planet in the solar system, Mercury orbits at an average distance of 37 million miles from the Sun. At this distance, Mercury has the largest orbital speed of any planet, racing around the Sun at an average speed of over 105,000 miles per hour. Earth, in comparison, moves at a speed of about 65,000 miles per hour. With a much smaller orbit than Earth, Mercury completes one full orbit around the Sun in only 88 days. As Mercury travels around the Sun, it also spins on its axis, like Earth does. However, Mercury has a stable resonance between its orbital speed and its rotation speed. This spin-orbit resonance means that Mercury's orbit and rotation have a fixed relationship, resulting in Mercury spinning on its axis 3 times for every 2 trips around the Sun. This interesting scenario means that although Mercury completes one spin rotation on its axis in 59 days, it actually takes 176 days to complete one solar cycle from sunrise to the next sunrise. This results in one solar day on Mercury actually lasting 2 Mercury years. While this extreme situation of days being longer than years is fine for the barren world of Mercury, it would be completely disastrous for life on Earth. Now, another extreme consequence of being so close to the Sun is that Mercury receives about 7 times the intensity of sunlight and solar radiation than Earth does at our distance. The intense levels of sunlight, compounded by the extreme lengths of daytime and nighttime, cause some of the most drastic temperature differences in all the solar system. The temperature reaches a blistering 840 degrees Fahrenheit on the daytime side, yet at the same time on the nighttime side, the temperature is a frigid minus 275 degrees Fahrenheit. Along with the intensity of sunlight, Mercury's proximity to the Sun also means that it is bathed in the intense radiation and high-energy particles that are streaming out from the Sun in the solar wind. Without the protection of a thick ozone layer or ionosphere, and having only an extremely weak magnetic field, Mercury is assaulted with levels of radiation that would eradicate any life. Once thought to be a completely barren and boring world, Mercury has shown that it still holds some amazing wonders of its own. For example, the possibility of a hot, molten interior and the persistence of a thin atmosphere restrict theories of any long evolutionary age to its history. When we look at Mercury, we see a unique planet existing in its own stable role in our solar system, characterized by planetary extremes. As one of the hottest places in our solar system, the day is hotter than the inside of an oven and the night colder than any place on Earth. The atmosphere on Mercury is by far the thinnest of any planet, barely measurable above the vacuum of space. With essentially no atmosphere, no water, and no way to escape the extreme hot and cold, Mercury could not sustain human life. God did not design Mercury to be our nurturing home, but He did with Earth. The planet Venus is the brightest object in the sky after the Sun and Moon. Records dating back to the Babylonian civilization reference Venus as a bright celestial object in the skies. Other civilizations, such as the Egyptian, Greek, and Chinese, include observations and cultural lore about Venus. Interestingly, historical references sometimes called Venus the morning star or sometimes the evening star. The ancient Greeks called Venus by 2 names, Phosphorus and Hesperus, supposing it to be 2 completely different objects. The 2-object idea isn't completely unreasonable, since for a portion of our year, Venus precedes the sun in the sky, so it will appear in the early morning just before sunrise. For the other portion of the year, it follows the sun, being one of the first objects visible in the evening. In fact, Venus is never more than 48 degrees from the sun, which is termed its greatest elongation. This alignment is due to its orbit being inside of Earth's orbit, closer to the sun. And in fact, 2 Peter 1 verse 19 makes reference to the day star that would rise when the day is dawning. In this verse, the words day star are translated from the Greek word phosphorus, which is a reference to the planet Venus. In more modern times, Venus has taken on the description of Earth's twin, or maybe Earth's sister planet. Venus is not only the planet that travels closest to Earth in its orbit, but it has such nicknames because it's nearly identical to the Earth in its size and its mass. However, Venus is an interesting case study in planetary characteristics, since in actuality it is extremely different from Earth in almost every other way. From a distance, we first notice that Venus is enshrouded in a thick atmosphere of clouds. This atmosphere is far thicker than Earth's. It's mostly composed of carbon dioxide and has an atmospheric surface pressure 90 times greater than Earth's. In fact, to experience an equal amount of pressure here on Earth, you would have to travel nearly 2/3 of a mile below the surface of the ocean. Such a depth is beyond free diving or deep diving without specialized suits or specialized vehicles to handle the immense amounts of pressure. Additionally, because of Venus's extremely dense atmosphere, we cannot see its surface without the aid of special imaging such as radar. In 1990, the Magellan spacecraft was sent into an orbit around Venus, and it began taking images using its radar altimeter. This allowed scientists for the first time on Earth to map the varied terrain of Venus's surface. In October of 1994, NASA lost contact with the Magellan satellite. But over the course of these 4 years, it was able to image 98% of the planet's surface. Beneath the thick clouds, Venus's surface shows signs of volcanic activity, possibly even presently active. In fact, a 5-mile-high shield volcano named Mont Mons has been revealed by the surface radar mappings. And although it's unclear if Mont Mons is still an active volcano, there are lava flows that can be seen extending across the plains to the base of the volcano. With Venus's thick carbon dioxide atmosphere and having a solar irradiance twice as high as Earth, Venus has the hottest average surface temperature in the entire solar system, over 860 degrees Fahrenheit. The extremely thick atmosphere also traps the heat in a greenhouse effect, so the temperature is pretty much always 860 degrees, whether it's daytime or nighttime. Such an incredible temperature means that liquid cannot be present on its surface. This is a stark contrast to Earth, where more than 70% of the surface is covered with water. Not only could liquid water not exist on the surface of Venus, but even metals such as lead and zinc would liquefy if they existed on Venus's surface. Another significant contrast between the two planets, Venus and Earth, is the presence of Earth's strong magnetic field. The rather fast rotation of Earth, once every 24 hours, is thought to maintain a steady and sufficiently strong magnetic field to provide a finely tuned cocoon from the dangerous streams of charged particles flowing from the sun. By contrast, Venus has an extremely slow rotation, once every 117 Earth days, and Venus lacks any magnetic field that could associate with protection from this dramatic solar wind. Although a few forms of life on Earth were designed to live in extreme environments, the entire planet of Venus would qualify as an extreme environment. The atmosphere of Venus is 90 times more massive than Earth's and maintains a world of very little variation and no seasonal changes. It also holds the record for the highest average temperature of any planet in the solar system, So without oxygen or water, having an extreme atmosphere, extreme heat, and no magnetic field to protect from dangerous radiation, Venus could not sustain life. While Earth was designed by God to bear a host of thriving ecosystems, He did not design Venus to be Earth's twin. Planet Earth, our home for all humanity, home for all the various kinds of life that roam its lands and swim through its seas and fly through its spacious skies. But have you fully appreciated the privileged place you call home? Daily life may not seem easy, but why is life even possible at all? Practically every physical parameter of our planet affects life, and every parameter has an impact on the others. If one parameter were different, a fraction larger or a fraction smaller, then all parameters would need adjusting to try and maintain balance. But the problem is that for life to exist, each physical condition must also fit within the narrowest of ranges. Too far out of range and life's possibility is completely lost. Earth exists as a privileged planet. One easy example for the balance of Earth's parameters can be seen in our distance from the Sun. Our world is a relatively warm, rocky-bodied, water-covered, oxygen-bearing planet. What would Earth look like if we orbited our Sun at a different distance? Well, our own solar system gives us insight. Closer to the Sun, and we might look like the barren, cratered, radiation-blasted world of Mercury, or the greenhouse gas-enshrouded, continuously hot landscape of Venus. No, the radiation intensity of our Sun means we need to orbit a good amount of distance away. But farther is not always better. If we orbited out near where the planet Mars resides, then our water vapor atmosphere would freeze, being unable to keep its moisture and its structure. At the distance of Mars, the Sun's warming light and heat would be reduced by over half, causing the majority of Earth's liquid water to be frozen sheets of ice. Earth's orbital path is in what astronomers call the habitable zone, or sometimes it's called the Goldilocks zone, because it is just right for the balance of life's necessities. But it's not just Earth's position that is privileged, because our planet still orbits a nuclear factory of sorts, our Sun, the nearest star. It is thought to derive its energy from nuclear fusion in its core, causing immense amounts of radiation to flow out to its gaseous surface, which in turn spews large amounts of heated matter into its atmosphere. In fact, every day, huge quantities of highly energized particles stream outward from the Sun through the entire solar system. How is it that with this immense amount of radiation and high-speed charged particles blasting toward Earth, that humanity is not in constant danger from this solar barrage? How is it that we are more concerned about a few clouds gathering in the sky than the enormous stream of solar radiation? The answer is Earth has been designed to exist right where it is. It has been equipped with multiple layers of protection, a custom-made cocoon of safety. And this cocoon of safety actually begins protecting Earth tens of thousands of miles away. The first layer in Earth's defense comes from the fact that we have a powerful magnetic field. The same physical process that helps a compass to always point toward the North Magnetic Pole also forms a magnetic field that surrounds the Earth. This magnetic field serves as a shield, forcing highly energized particles away from Earth. As the energized particles hit the magnetic field, the largest portion of them are deflected around and onward into space. A few particles become trapped in the magnetic field, and they're funneled inward from space toward the Earth's poles, where they interact with the upper atmosphere, releasing their energy in the form of light. And we see them as the auroras the northern and southern lights. Now, a second layer of defense designed for life's preservation can be seen in Earth's ozone layer. This layer of the atmosphere is composed of a special arrangement of 3 oxygen atoms that form one molecule, ozone. This layer effectively filters the most dangerous forms of ultraviolet radiation in the sun's spectrum. This form of radiation would be extremely harmful to life, especially humans, if it were not greatly reduced by this layer in our atmosphere. Ultraviolet light still passes through the atmosphere, but at much different levels than above the atmosphere. Much of what astronomers know about the ultraviolet radiation from distant objects in space has only been discovered in the last few decades, because Earth's atmosphere is so good at filtering this form of radiation. It took space telescopes and probes launched outside the atmosphere to fully detect it. The third layer of defense relates to the overall structure and density of our atmosphere. Earth's atmosphere is structured in such a way as to serve multiple functions, including layers dense enough to absorb X-rays and ultraviolet rays, an ionized layer to protect from charged particles, layers with very little internal movement, and layers with large amounts of convective currents. The overall density of the atmosphere is enough to maintain good percentages of oxygen and water vapor, but not so thick that the cycles of life would be disrupted. Now we can see from Earth's protective layers to its privileged position, to every physical parameter that defines our planet. Earth was designed by the intelligent Creator to be just right for life, to not only exist, but to live and thrive. As described in the Bible in the book of Genesis, God focused during the creation week on creating and preparing Earth to be an inhabited world. During days 1 to 4, God made water, air, land, plant life, the sun, and the moon, all of which are vitally important to the existence of humanity. We see from Proverbs 3, verse 19, that the Lord by wisdom founded the earth. By understanding, He established the heavens. The book of Isaiah tells us that God did not create it in vain, but formed it to be inhabited. God made earth as a privileged planet, as the habitable home for human life. He placed our planet at the perfect distance from the sun, gave it a life-sustaining atmosphere that protects us from harmful solar radiation, and surrounded Earth with a protective magnetic field that deflects dangerous charged particles from space. Surely we can say there is no better home for humanity anywhere throughout the heavens or beyond the stars. When we think about nighttime, one of the first images that comes to mind is the large full moon shining bright in the darkness. The moon is Earth's nightlight, and by far the brightest object in the night sky, many times brighter than even the brightest stars. While the moon is the luminary that lights up the night, it's interesting and important for us to observe. The moon actually does not produce its own light like the sun does. The sun is composed of gas and ionized atoms that are heated so much that they emit various forms of energy, including the visible light we see on Earth. The moon, on the other hand, is a solid, rocky body with a cold, barren surface. No atmosphere, no liquid water. The moon's surface that we can see quite well, especially through binoculars or telescopes, is simply reflecting light from the sun. Similar to a mountain range off in the distance that we see, not from the light that it emits on its own, but reflecting the sunlight. In contrast to the brightness of the sun, the moon is the lesser light, but the moon truly does rule the night. Within the solar system, the Earth-Moon relationship is rather unique. In comparison to the other planets and their moons, our moon has the largest ratio of moon to planet size and diameter to orbital distance. What this means is that the moon has both a larger physical size in relation to Earth and a larger apparent visual size in our sky than any other moon-planet system. These simple relationships provide the foundation for the moon's functional and finely tuned role as Earth's nearest companion. One of the most obvious roles the moon provides is its timekeeping status. As the moon orbits around the Earth, it progresses through a sequence of lunar phases, where the moon's appearance slowly changes by how much it's illuminated by the sun's light. Beginning with the completely darkened new moon phase, this 29.5-day lunar cycle goes through a progression from waxing crescent to first quarter moon to waxing gibbous to its maximum illuminated state at the full moon. Then it begins to diminish into the waning gibbous, the third quarter moon, the waning crescent, and back to a darkened new moon. For many cultures, past and present, the lunar cycle formed an obvious timekeeping foundation by which their calendars could be based. In fact, the words moon and month share etymological origins, as the 29.5-day cycle helped define the changing of months. At a more basic level, though, the moon's nightly phases serve as a rhythm for the natural world. Nocturnal behaviors of animals, from insects to birds to mammals to even marine species, have been linked to the monthly cycle of the moon. Now, the phases of the moon are caused by the relative positioning of the sun, the earth, and the moon. As the moon travels in its orbit, it progresses from being on the same side of the earth as the sun, causing the new moon, to being on the opposite side from the sun, causing the full moon phase. While the orbits of the moon around the earth and the earth around the sun are not exactly aligned, there are specific points where the orbits cross. When the moon passes through these points in its minimum new moon or its maximum full moon phase, Earth is treated to a stunning eclipse event. Lunar eclipses occur only during the full moon phase, where the moon's orbit crosses precisely behind the Earth, passing through its shadow. For several hours, as the Earth's shadow covers the moon, the nighttime side of Earth is treated to the bright full moon turning a dark reddish orange. On the other hand, solar eclipses occur only during the new moon phase, when the moon passes in a precise alignment between the Earth and the sun. Though the sun is 400 times farther away than the moon, and is also 400 times larger than the moon, this exact proportion results in the sun and moon being the same angular size in our sky. The size proportions, along with the precise orbital alignments, allow solar eclipses to be one of the most dramatic natural phenomena experienced. For several hours, the moon creeps in front of the sun, until for a few brief minutes, the sun's bright surface is completely covered by the moon. These few dark moments within a total solar eclipse are the only moments when it is safe to look at the sun without specialized protection. And it's only during this time that you can visually see the upper layers of the sun's atmosphere. Since it requires such a precise alignment, each total solar eclipse is only visible for a few minutes to the region where the moon's shadow casts as it travels across the Earth's surface. For those who are in this narrow strip, the encounter is a full sensory experience. The sky darkens and stars become visible. The temperature drops noticeably by several degrees, and the sounds of nocturnal animal life begin. As a timekeeping element, it is easy to see how the unique experiences of lunar and solar eclipses could be used as markers in history. The consistent and regular presence of the moon's cycle forms the foundation for nature's nocturnal cycles, but includes these incredible eclipse events as a punctuation in time. Beyond its effect on time and natural cycles, the moon plays an absolutely vital role for existence and the health of life on Earth. Both the Earth and moon exert a gravitational force on each other. Earth's gravitational force is much stronger and it dominates their interaction, which is why the moon orbits around the Earth. However, the moon's gravity has a crucial impact on Earth and even in our very lives. If you've ever been to an ocean beach or a coastline, then you have seen the effect of the moon's gravity, the tides. Even though the moon is at a great distance from Earth, approximately 240,000 miles, its gravitational force produces the ocean's tides. Each day, all around the globe, high tides and low tides are seen all along Earth's coastlines. This natural cycle of the ocean's level rising and falling produces positive benefits for life on Earth. Every day, beaches are swept across with incoming and outgoing waters, and these waters bring nutrients from farther out in the ocean for creatures that live in the shallows or the tidal pools. The outgoing tides can serve as a means of cleansing, refreshing the coastal regions. They can take minerals and salts back out to the deeper waters. The tides as a whole benefit from the impact of the circulating currents driven by the daily cycle of the moon's causing of these tides. With over 70% of Earth's surface covered by oceans, the impact that the moon plays directly on life cannot be underestimated. The moon is beautiful to observe, a constant nightly companion. While the moon fulfills its role of lighting the night, it also serves key roles in the cycles of life. The moon has served as a timekeeping element for both animal populations as well as human civilizations throughout history. Through its precise size and orbital alignments, the eclipses have punctuated history with dramatic observational experiences. In its formation of ocean tides, the moon has far-reaching effects for sustaining sea life, influencing coastal conditions, and even affecting the atmospheric conditions. As the only body outside of Earth that man has personally landed on, set foot on, and explored, our relationship to the moon may be greater than any other celestial body. Created by God, the moon has a designed role to support the balance of life here on Earth. The next planet out from Earth's orbit is the red planet Mars. Even without the aid of telescopes, Mars is easily seen and recognized in the sky by its reddish color. Because of its striking color and relative brightness in the heavens, Mars has intrigued observers throughout history. Today, through modern scientific studies, we have gained a much greater wealth of understanding for the red planet. Even that its characteristic color comes from sunlight illuminating the planet's reddish-brown, iron-rich soil. Now, when considering Mars as a planet, it has many similarities to Earth, as well as having some drastic differences. Much like Earth, Mars has varying geological features, including desert plains, valleys, deep canyons, and various mountains. Yet despite Mars being half the size of Earth, it is home to a mountain 3 times taller than Mount Everest. Named Olympus Mons, this mountain is the tallest in the whole solar system, extending 17 miles above the surface. Mars also has Valles Marineris, a canyon feature similar to Earth's Grand Canyon. However, Valles Marineris is huge, much larger than the Grand Canyon. It's approximately 2,485 miles long, meaning it would stretch across the entire continental United States from New York to San Francisco. It's also up to 7 times deeper than the Grand Canyon. These features show both a similarity but also the uniqueness of the Martian landscape. Further similarities include the angle of Mars's axial tilt, being very close to Earth's inclination also, allowing for similar seasonal variations, and also the length of the Martian day from sunrise to sunrise is only a few minutes different from Earth's 24-hour day. Mars also has regions of ice at its poles, though not water ice. It also has varying atmospheric weather patterns and even small local atmospheric disturbances such as tornadoes or dust devils. However, there are also some very extreme differences between Earth and Mars. One obvious difference is the barren, desert-like landscape that dominates Mars. there are no oceans, no lakes, no rivers to be found, which is a stunning contrast to the vast quantities of liquid water covering Earth's surface. With no water and no plant or animal life, Mars can have enormous runaway global dust storms, which floods the entire Martian atmosphere with dust, completely obscuring our view of its surface. Over the years, there have been many investigations into the possibility of liquid water on Mars, but without any clear evidence. Even if water or water ice is found on Mars, the contrast between the Earth's over 70% coverage of deep and expansive oceans to Mars having none on its surface is a drastic distinction. What makes the contrast even greater is the fact that the Martian atmosphere would restrict the existence of liquid water over any substantial length of time. The atmospheric pressure on Mars is over 100 times lower than Earth's atmospheric pressure, and the average surface temperature is around minus 60 degrees Fahrenheit. For the majority of Mars's surface, water could not even exist in a liquid state. Further comparing Mars's atmosphere to Earth's, we find that it is a complete opposite ratio of oxygen to carbon dioxide. On Mars, carbon dioxide forms about 95% of the atmosphere, with oxygen and water vapor only accounting for less than 0.2%. Here on Earth, oxygen accounts for about 21%, and carbon dioxide only accounts for about 0.04%. Thus, Mars lacks the necessary atmospheric environment to support any significant amount of liquid water on its surface. Given the extremely thin, carbon dioxide-dominated atmosphere, the desert-like landscape, the huge temperature extremes, and only a very weak global magnetic field, any considerations for manned space missions to Mars will need to take into account that we will be leaving our uniquely designed, life-supporting planet behind. While in many ways Mars has a less hostile environment than Mercury or Venus, it in no way is life-friendly or characteristic of a world intended for life. While Mars is not specifically referenced in the Bible, its created purpose can be contrasted with Earth's. The Bible says that Earth was created to be inhabited, according to Isaiah 45, verse 18. While the creation of Mars falls within the general context of the stars or the luminaries created on day 4, with their purpose being to serve as signs and seasons. Being one of the brighter objects in the sky and having a distinct appearance, Mars has certainly played an important role in the history of many cultures: Egyptian, Babylonian, Greek, Roman, and others. As such, it has certainly fulfilled and continues to fulfill one of its primary created purposes: to serve as a sign or a marker in time's progression. Jupiter is the king of the planets in our solar system, being by far the most massive and larger than any other in the solar system. Jupiter is the 5th planet out from the Sun, and 5 times farther out than Earth, orbiting beyond the asteroid belt that divides the inner terrestrial planets from the outer gas giants. Although its distance from Earth varies throughout the year, Jupiter's enormous size allows it to still be one of the brightest objects in the night sky, brighter than any star. As such a bright object, Jupiter has a long history of being observed, but it wasn't until the invention of the telescope that Jupiter's true, stunning beauty and intriguing design became known. Jupiter's physical parameters are impressive. Its diameter is approximately 11 times larger than Earth's. Its mass is almost 2.5 times greater than Mercury, Mars, Venus, Earth, Uranus, Neptune, and Saturn combined. And due to Jupiter's monstrous mass, the force of gravity you would feel at the top of Jupiter's atmosphere would be about 2.5 times greater than here on Earth. This means that if you weigh 200 pounds on Earth, you would weigh 500 pounds on Jupiter. Now, Jupiter is a drastically different kind of planet from Earth. Earth is a terrestrial planet, meaning it has a rocky surface, and that defines the majority of its size. Jupiter, on the other hand, is classified as a gas giant. It has no visible solid surface, and its size is dominated by an extremely thick and dense gaseous atmosphere. Jupiter's atmosphere is composed of various layers of gas, preventing us from seeing very deep into the atmosphere. Even looking through a small telescope, you can see the outermost layers of Jupiter's atmosphere, and they're visible as distinctly impressive bands. The alternating light and dark colored bands are caused by the turbulent winds and the storms that stir up different varieties of gases, and they cause the clouds to rise and to fall to different heights. Probably the most recognizable and fascinating feature on Jupiter is its Great Red Spot. Named for its appearance, this giant oval-shaped storm in Jupiter's atmosphere has existed as far back in time as telescopes have been able to observe it. In many ways, this storm is similar in structure to hurricanes that we have here on Earth, but far more extreme and gigantic in proportion. It has a size 3 times larger than our entire planet and reaches wind speeds almost 400 miles per hour. The amazing turbulence of Jupiter's atmosphere is driven in part by Jupiter's rotation speed. While Earth takes 24 hours to make one rotation on its axis, the much larger Jupiter makes one rotation in less than 10 hours. This incredibly rapid rotation makes Jupiter the fastest rotating planet in the solar system, and it sets up the conditions for the Great Red Spot, along with other extreme atmospheric conditions. King of the planets, Jupiter is also a host to an impressive array of moons. More than 60 moons have been discovered orbiting around Jupiter. These moons vary in all shapes and sizes, from irregularly shaped moons, only a few miles in diameter, to Ganymede, the largest moon in the solar system, one that is even bigger than the planet Mercury. Of all of Jupiter's moons, the most well-known are the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. And these 4 moons are Jupiter's largest and even big enough to be visible in backyard telescopes. The extreme diversity of all the moons can easily be seen in these 4 examples. Io is a violently active moon with the greatest amount of volcanic activity in the whole solar system. Some of its volcanoes spew gases and vapors hundreds of miles above its surface. On the other hand, Europa is a world that is encased under a frozen surface. The largest moon, Ganymede, is a cold and rocky world with a diameter over 3,200 miles wide. And last of all, the darkest and the farthest out of the Galilean moons, Callisto, is the most heavily cratered object in the solar system. Fire, ice, rock, and craters. Jupiter and its system of moons are an incredible testament to the existence and functional complexity and fine-tuning of the laws in our cosmos. With its multitude of orbiting moons, having variation in size and scale and composition, the Jupiter system resembles a miniature solar system. Yet the same physical laws that maintain Jupiter's complex system also govern the larger arrangement of our solar system, and ultimately the cosmos as a whole. As we study this small-scale yet analogous system, we see that these celestial bodies demonstrate an intelligence behind the order in operation, and they attest to God's creative nature. Saturn is probably the most recognizable planet in our solar system. With large, bright rings encircling it, it is the 6th planet from the Sun and the 2nd largest gas giant, about twice as far from the Sun as its nearest neighbor, Jupiter. Saturn is an intriguing planet, with its size, its wide rings, and its diversity of moons. While all of the gas giant planets have ring systems, Saturn's is by far the most prominent. Once thought to be a solid structure, The rings of Saturn are actually composed of billions of small objects. The size of the particles varies greatly, from tiny clumps of ice to boulders larger than an automobile. Since the rings are a collection of individual objects, each particle, clump, or boulder is following its own gravitationally bound orbit around Saturn. Now, the large-scale structure of the rings we see has been divided into 7 ring groups with various gaps observed between them. There are 3 prominent rings, A, B, and C, and there's 4 fainter rings, D, E, F, and G. The rings were given these letter designations in the order of their discovery. As a matter of the dark gap seen between A and B, it's named the Cassini division after its discoverer. It measures 2,920 miles wide, which is just about wide enough for the planet Mercury to orbit inside that gap. So you can see just how enormous Saturn's ring system is. Its full width extends approximately 350,000 miles across. Yet this massive collection of billions of particles spanning hundreds of thousands of miles across is so balanced by the laws of gravity that its thickness is less than half a mile. This razor-thin geometry, at least on the scale of Saturn, induces a seeming optical illusion every 15 years or so when Saturn's rings disappear. This is known as a ring plane crossing, and the ring orientation becomes edge-on, so that you are looking exactly along the ring's plane. Through history, the times of Saturn's ring plane crossing from Earth's vantage point have been periods of great discovery. You see, with the beautiful and stunningly bright rings out of view, Saturn's system of moons can be probed with greater effectiveness. Prior to the era of satellite missions, numerous of Saturn's moons were found during these periods. And Saturn has lots of moons, in the neighborhood of over 60. Of these moons, Titan is the largest, and it's the second largest moon in the entire solar system, larger than the planet Mercury. Interestingly, Titan is the only known moon in our whole solar system to have a dense atmosphere. Even though it is large and has been observed for a very long time, very little was known about this moon. That is, until the Cassini satellite arrived in its orbit in 2004. It began its long mission orbiting around Saturn, and one of Cassini's primary missions was to study the moon Titan. The satellite released a separate probe named the Huygens probe, which entered into the atmosphere of Titan and descended to the surface. This probe gave astronomers a way to study the amazing features of Titan. And Titan turned out to be an extreme world, where its surface has been shaped by rivers and lakes of liquid ethane and methane. Saturn is an excellent example of the magnificent beauty and order in the cosmos. As one of the most recognizable planets in the solar system, Saturn and its ordered system of rings and moons reflects the design given by the great designer. Everything God created is meant to reflect His glory, and Saturn is no exception. As it says in Psalm 66, "Come and see the works of God." The last 2 planets in our outer solar system are Uranus and Neptune. These 2 planets are very similar. Both planets are classified as gas giants. They have similar overall appearances, have many moons, faint rings, and are very cold. While they have similar atmospheric compositions, there is a difference in their overall density. Uranus is slightly larger in diameter, but Neptune is slightly more massive. Each planet presents some unique characteristics as we consider their roles in our solar system. First, Uranus is a sideways planet. Where Jupiter's poles have only a very slight tilt of degrees, and Earth's axis is tilted 23.5 degrees, Uranus is tilted about 98 degrees from vertical. This extreme planetary tilt means the sun's light shines directly on the polar regions for much of its orbit. Since the planet rotates in this sideways fashion, each hemisphere experiences constant daylight, 1/2 of its orbit, which totals 84 Earth years. When we consider the most distant planet, Neptune, we find that it has a highly active atmosphere. While Jupiter's winds reach speeds of 400 miles per hour, Neptune has the highest atmospheric wind speed in the entire solar system, reaching speeds nearly 1,200 miles per hour. Like all of the gas giant planets, Neptune has a rapid rotation, especially for its size, completing one rotation every 16 hours. Like Jupiter with its Great Red Spot, Neptune also has been observed to host a giant storm. One such storm, observed by the Voyager 2 space probe in 1982, was named the Great Dark Spot. This storm had a size equal to Earth's diameter. In contrast to the persistence of Jupiter's large storm, Neptune's Great Dark Spot has since disappeared. But with violent atmospheric winds, it won't be the last disturbance seen. An additional quirk seen for both Uranus and Neptune is that their global magnetic fields are significantly tilted with respect to their rotation axes. So the poles of the magnetic field are substantially different than the poles of rotation. This contrasting alignment results in both planets having a highly complicated magnetosphere, caused by the magnetic field becoming twisted and distorted as it is rotated onto itself. As we see on Earth, the magnetic field plays a vital role in protecting and shielding the planet from the high-energy charged particles in space. Life on Earth would have serious complications if this type of scenario existed here. Now, when we consider the role these two planets have in our solar system, their existence is forever intertwined. Through history, many civilizations have made note of the existence and the position of the inner planets: Mercury, Venus, Mars, Jupiter, and Saturn. These 5 objects would be known as wandering stars because, although their appearance in the sky was like a star, their movements wandered along different paths. Thus, the discovery of Uranus as a similarly wandering object in 1781 was the first discovery in thousands of years, and it was made possible by the telescopic invention. Uranus became intensely studied over the next half-century. Its orbital parameters were slowly calculated and refined. However, by the early 1800s, astronomers had already noticed that there were significant differences between the calculated and the observed locations of Uranus. Now, the law of gravitation, supplied by Newton, the laws of planetary orbits described by Kepler, had aided astronomers for nearly 200 years to make accurate and calculated predictions of the known planets. Acknowledging that the cosmos is orderly and that it operates through regular functionality, astronomers and mathematicians began calculating and predicting the position of an unseen planet that could be the culprit inducing the differences in Uranus's location. From these precise predictions, the planet Neptune was discovered in 1846. During the creation week, God set laws in motion that governed our physical universe, including the planets. These laws serve as regular and calculable guides to the functioning of our solar system. Utilizing hundreds of years of knowledge from scientists studying God's creation, 19th century astronomers were able to observe and predict clues that led to the planet Neptune's discovery. Uranus and Neptune provide intriguing examples of planetary dynamics and have served well in their role of proving the intelligent design of our cosmos. Throughout history, astronomers and observers of the sky have acknowledged that the stars scattered across the heavens display an incredible diversity in appearance. So much so that the naming of individual stars has been found throughout ancient civilizations and was used to tell stories, mark the time of historical events, and map changes seen in the heavens. When looking at the stars, the two most easily observed traits are their variety of brightnesses and their colors. Even to the unaided eye, the difference in brightness between the brightest and the faintest stars is over a factor of 600. The colors of stars can also provide dramatic distinctions. Stars are not all simply white points of light, but instead can be bright orange or reddish, yellow like our sun, or a bright bluish white. The color of a star corresponds with its surface temperature. Similar to how the color of a fire's flame shows how hot the fire is. If a star is very hot, it will appear blue-white, while on the other hand, a cooler star will be red in color. Of course, stars are not exactly like the flames of fire we usually see. Instead, the objects we call stars today are extremely dense collections of gases, mainly hydrogen and helium. These intensely hot bodies of plasma emit tremendous amounts of energy, some of which is visible light. Despite fundamental similarities, the diversity of stars is astounding. In the late 1800s, Annie Jump Cannon, a female astronomer at Harvard, painstakingly worked to classify approximately 400,000 stars into a systematic framework. Today, the basis of her work can be seen in the stellar type designations using the letters O, B, A, F, G, K, and M. Listen to how she described her work and what significance it would provide. Classifying the stars has helped materially in all studies of the structure of the universe. No greater problem is presented to the human mind. Teaching man his relatively small sphere in the creation, it also encourages him by its lessons of the unity of nature and shows him that his power of comprehension allies him with the great intelligence overreaching all. The work of Cannon, Pickering, and their contemporaries helped to quantify how truly diverse stars really are. Building upon their success in surveying stellar types, two early 20th century astronomers, Hertzsprung and Russell, began to see amazing relationships when comparing the spectral types Cannon had developed with the absolute brightnesses of the stars. When they plotted the spectral type against its absolute brightness, distinct groupings of stars became apparent. Today, these groupings generally categorized into the following classes: dwarf stars, main sequence stars, giants, and supergiants. Within each of these groups, there are sub-classifications that distinguish even more of their stellar complexities, such as white dwarfs and red dwarfs, red giants and blue giants, and numerous types of variable stars. This classification chart continues to be an important tool and is referred to as the Hertzsprung-Russell or HR diagram. When you look at the HR diagram, probably the first pattern you notice is that most of the stars form a diagonal line across the plot. This grouping is called the main sequence and provides an interesting relationship that simply says hot stars are generally brighter than cool stars. Exceptions to this rule do exist, and when studied, we find that they often have some extreme characteristics. Main sequence stars are often considered as the more usual or typical group of stars, and our Sun is located about in the middle of this main sequence. White dwarfs are stars that fall well below the main sequence line, and like their name suggests, their radius is small, being about the same size as Earth's radius. However, their white color tells us that they have a very hot surface temperature. On the other hand, giant stars are larger and brighter than those on the main sequence. On the HR diagram, you will find these stars above the main sequence line. Supergiant stars, as their name indicates, are even bigger than giant stars. The largest stars are typically supergiant stars that can be upwards of thousands of times bigger than our Sun. But because of their red color, they have much cooler surface temperatures. If you were to look in the night sky at the constellation of Orion, you would see a bright red supergiant star. Orion is often one of the most obvious constellations to identify, and it can best be seen during the winter months in the northern hemisphere. One of the easiest ways to identify Orion is by locating the line of 3 relatively bright stars that form Orion's belt. Once you have located the 3 belt stars, the red supergiant star is located up and slightly to the left, about where you would expect Orion's right shoulder to be. This star, named Betelgeuse, will appear as one of the brightest stars in the Orion constellation. If you were to place Betelgeuse into our solar system, right where the Sun is, it would extend outward beyond Jupiter's orbit. If you continue looking at the constellation of Orion, but this time look towards the bottom right, about where Orion's foot might be, you'll see a blue star called Rigel. This star is a blue giant, which means that it is much larger than the Sun and also has a surface temperature about 11,000 Kelvin, many times hotter than our Sun. Thinking back to the HR diagram, both of these stars will be well above the main sequence line in the giant and supergiant regions. However, due to their vastly different colors, they will be at opposite ends of the temperature scale. In 1 Corinthians chapter 15, the Bible uses the great diversity of stars to teach a spiritual lesson about our souls. It says, "There is one glory of the sun, another glory of the moon, and another glory of the stars. One star differs from another star in glory." The Christians in Paul's day could easily understand this analogy. Today, we also can understand it, and maybe even to a greater extent, as we see how diverse, ordered, and designed the stars in our universe really are. In modern astronomy, we now understand that the cosmos is filled with a vast array of objects beyond the stars. The invention of the telescope over 400 years ago expanded our view of the universe and revealed that even more complexities exist beyond what we can see with our eyes alone. Since its invention, scientists have used telescopes to methodically search and catalog not only the stars, but the ever-increasing number of different objects. As telescopes improved and their ability to gather light became better, an array of faint, extended objects became visible, such as distant comets in our own solar system, clouds of gases surrounding single stars, bright nebulas hosting clusters of stars, and curious, faint nebulas of a different form. Now, this last class of faint nebulas became intriguing to understand, whether they were simply small, faint, nearby nebulas, or whether they could be very large, distant nebulas. As these faint nebulas were observed and more of them looked at, it became apparent that many had different structures, and there were differing types of them. Of special interest were the so-called spiral nebulas, which displayed a varying degree of overall spiral pattern within their cloudy structures. One of the largest, most studied spiral nebulas was called the Great Andromeda Nebula. By the early 1920s, astronomers now had evidence that these spiral nebulas were actually very distant collections of stars and gas and dust gravitationally bound together. The composition and structuring of these very distant objects were similar to what was here in our own Milky Way galaxy. From this discovery, the size of the known universe exponentially increased. If the stars and nebulas within our own galaxy are separated by great distances, and we can now look out into space and see not only one, but a multitude of other galaxies, then our cosmos truly is vast. With this new class of object now identified, the thrill of exploring God's creation exploded. The race was on to find more galaxies and to probe deeper into the diversity of their structures. After decades of study, what we know about galaxies and their structure is stunning. Estimates for the number of galaxies in our cosmos are ever increasing as larger and larger telescopes are constructed and deeper surveys are conducted. To think that within the span of 100 years, we went from knowing about one galaxy, our own, to now estimating the existence of hundreds of billions, maybe even trillions of other galaxies. Yet, even with the incredible number and the vast diversity, we are still able to see the order and functional complexity that exists within the laws and the matter of our cosmos. Now, several classification frameworks exist for comparing and contrasting galaxies, but by far the most well-known and first developed was by Edwin Hubble. His very basic classification framework included two main sequences: elliptical galaxies and spiral galaxies. Galaxies which didn't fit into either of these two major types were simply termed irregular galaxies. The Hubble system uses the visual structuring of galaxies to determine their classification. Elliptical galaxies are overall rather featureless, and they form a sequence of shapes from a spherically symmetric, like a basketball, to an elongated ellipsoid, like an American football. There are 8 major subdivisions labeled E0 to E7 that account for the variation between these extremes. Spiral galaxies, on the other hand, have lots of visible structuring. 2 major subclassifications of spirals exist. They're called normal spirals and barred spirals, where a barred spiral has a large bar-like structure stretching across its nucleus. Barred and non-barred galaxies are then subdivided in the same fashion, depending on how tightly wound the spiral arms are and how big the nucleus is. Based on the Hubble classification system, if a galaxy has tightly wound spiral arms and a large nucleus, it's given a subdivision labeled by the letters capital S, lowercase a. As the spiral arms are less tight and the nucleus is smaller, the designations progress alphabetically from SB, SC, and SD. From just this simple means of classifying galaxies, we can begin to appreciate how the laws of our universe provide for the existence of a diversity of galaxies. Beyond the stars we see in our sky is a cosmos defined by its design and purpose. As participants within the universe, our role is not as natural creators, but rather observers, seeing the cosmic design that surrounds and supports our lives.